Are you sure this is the right place?
Yeah, the mysterious object you found in part 0 and we never mentioned again seemed to be attracted in this direction. Aha! Here it is! Honestly, even I'm not really sure what's in here, and I'm the one who's writing this stuff.
Maybe you need some time to think about the content.
Yeah. Hey, I think I sense a problem coming up.
Really?
In 3, 2, 1.
Angie's, are you okay?
Yeah, it's just that vector calculus is the subject I didn't do a good job in the exam for.
I'm so sorry to hear about that.
Yeah. Anyways, I guess I need to explain what this is. You understand that an integral is the infinitesimal sum of all values of a function in a given bound. A double integral does this for a section of 2D space. In addition, this other symbol tells you the integral over a curve parametrized by x. What Green's theorem states is that for any closed curve that doesn't cross over itself, if p and q are functions of x and y, then the line integral of p on the curve parameterized by x plus the line integral of q on the curve parameterized by y is equal to this double integral over the region that the curve encloses, provided that the curve is going counterclockwise around the region.
Also assuming that p and q have continuous partial derivatives. We don't want it to give an invalid result after all.
So, here's how we're going to do this. We are going to split this problem up. If it can be shown that the line integral of p along the curve parametrized by x is equal to the double integral of minus the partial derivative of p with respect to y, and the same goes for this one, then we can add them together and prove Green's theorem. Furthermore, we are going to assume that the boundary can be parameterized by either this or this. That is, no concaveness.
These two are symmetrical along the y equals x line, and reflecting it also changes the direction of travel. That means if we can prove one, it can easily prove the other by swapping x and y and negating one side. Let's try tackling the first one.
First, try calculating the right-hand side of the expression.
Okay, using the fundamental theorem of calculus, the middle part is just negative p of xy, where y ranges from g1 of x to g2 of x. So substituting the bounds in, we get that it's equal to p of x and g1 of x minus p of x and g2 of x.
Okay, stop. That's all we need. Now it's time to tackle the other side. Let's break the curve down into 4 parts. C1 will go from the bottom left-hand corner to the bottom right corner. C2 will go directly up into the top right corner. Then C3 will follow G2 to the top left corner, and C4 will go straight down back where it started. Note that the lengths of C2 and C4 may be 0.
That makes C1 and C3 easy to calculate since both of them were parameterized by G1 and G2 respectively. C1 goes from x equals a to x equals b, and C3 goes from x equals b to x equals a. We better negate that.
C2 and C4 are also easy to calculate since x stays constant there. You can see if you replace dx with dx over dt dt, since x is a constant, the derivative of x is always 0, so the integrals are 0. Adding the integrals, we can see that it's the same as what we showed before.
As we said before, the proof for the other half of the equation is similar. So we proved it for convex shapes.
But Green's theorem holds for all shapes, so we're gonna have to prove that. Let's take this spoon shape as an example. We can break these apart into convex shapes, and the double integrals within the big shape is equal to the sum of the integrals in the smaller region. It's a good thing that this crescent can be broken up into just 2 convex sections. Let's break the bordering curve of these regions into 2 parts. The sum of the 2 line integrals can be written like this. Now, do you notice anything strange about these 2 parts?
I do actually. One is just the upper book. If we parameterize them with respect to t, where t goes from 0 to 1, it's easy to show that c2 of t equals c1 of 1 minus t, so it's just equal to this. And so now we can join the endpoints, and this is just 0.
And the other 2 curves form the boundary curve of the big shape. So, Green's theorem works. And since Green's theorem holds if you add 2 regions together, then it must hold if you add any number of them.
Hey, what applications does Green's theorem have anyway?
Land surveyors use it to find the area of weirdly shaped plots of land. If you let p equal to minus y and q equal to x, this just becomes this, which is twice the area of the region. A device known as the planimeter uses this property. You can watch all about it in this video.
That's great and all, but we need to link it to complex numbers for the door to open, remember?
Well, we're dealing with functions that require two real numbers. You know what else requires two real numbers? That's right, a complex number. For a complex number z, where z is equal to x plus iy, it's easy to see that dz is equal to dx plus idy. So given a complex valued function f of z, this can be written like this. If you apply Green's theorem, then you get the W integral of I dabba f over dabba x plus dabba f over dabba y. This is Green's theorem for complex numbers, so it's usually written like this.
There we go, the door has opened. This was a pretty short video, so... whatever. Let's just go in. I don't really have time.